do that anyway, just in case. Okay, so we're in the middle of this problem of showing what finding that three vectors are a basis, and that we have a constraint. So if we have a constraint, B, the set B of V1, V2, and V3 above does not span space. But how do we show that? How do we conclude? Well, what we say is we need a counterexample. To show, we need a counterexample. We need a vector that cannot be represented. Well, we can choose one. We can choose one to find a counterexample. We can choose AX equals AZ equals 0 and AY equals 1. Therefore, the third equation becomes 0 equals 1. Now, I can, what's going to happen here is t is a free variable, and I could solve for s. For example, s is going to equal ax minus t, and r is going to equal az minus s. Well, we want this is minus this stuff, so we want to do the minus sign, so we can't. R is going to equal minus this plus this. So here's sort of our basic solution. Here's the way we would solve this. We'd say, well, we have these three equations, and we want to choose. Oh, sorry about that. Let me just do this properly. We want to then put S in for his because we're solving for R equals minus AZ plus AX minus T, and S equals AX minus T. So there we've solved for the leading variables RS in terms of the free one. So I choose any T I want, and I get R and S. And then I've chosen those three variables, but no matter what I choose, this is always a contradiction. So I can never make that true. That's always false. Therefore, there's no way to choose RS and T. And what you want to say is, the way you want to do it is you want to say, well, look, here's a counterexample. Here is this vector, 0, 1, 0, and it cannot be represented. There's no way to choose RS and T so that this is true. So this is true. Okay, so therefore, the conclusion is once you have the counterexample, B, so the final result is B does not span R3C. Even though it has three vectors, it doesn't span the space. Okay, well, you could stop there, but because sometimes you can still ask, well, maybe they're linearly independent. So that's another thing we could ask: are those three linearly independent? Well, what you do with that is you don't have to go back and solve it all again, because what linear independence? This is part 2. Linear independence. Now, what you need to show there is you need to show that R times V plus S times V plus V1, 2, and 3 for those three vectors above. If this equals 0, then R, S, and T equals 0. That is the only linear combination. The only way to make this 0 is if R, S, and T are 0. So the way you prove a conditional is to suppose that RV1 plus SV2 plus TV3 equals 0, and then show that RS and T are 0. Well, this equation here is just this equation with all of these three 0. So linear independence is a special case of spanning the case in terms of the technology. Okay, so what that means is I can go through and say, well, this is the augmented matrix with these 0. Okay, now what that means is I can reduce that matrix to row echelon form, and because these are all zeros, that just amounts to putting in zeros over here. So the row echelon form of this last equate of this last the row echelon form version of the augmented matrix of this system is going to be -1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, because I'm choosing the values 0, 0, and then ax is 0, ay is 0, z is 0, so all three are 0. So the question, if I assume this is true, then there must be then the only way that can happen is if this is the solution. This linear system is represented by this augmented matrix in echelon form. Okay? So then I can say, okay, well, does this have a non-zero solution? Because if it has a non-zero solution, then that means that this could be true and this could be false, so that this implication would be false. Let's see who has there. Okay. So let's solve this system again. Well, that is S equals minus T. That's from the second equation. And the first equation is minus R equals minus S. So that becomes R equals S equals minus T. So R equals minus T, S equals minus T. And so all I have to do is find a solution of this system for RS and T where RS and T are not 0. And it's true, I can find one. I can choose T equals 1 and R equals S equals minus 1. So if I choose those three values, this linear combination equals 0, but RS and T are not 0. So therefore, RV1 plus SV2. So therefore, you found a case in which, let me see, this is R, S, and T, minus 1, plus 1, minus V3 equals 0, and R, S, and T are all greater than 0. So the linear independence conditional has a premise that's true and a condition that's false. Therefore, the conditional, the if-then statement, is false, and B is also not linearly independent. Okay, so just to make these video things shorter,